already covered up more than two modules. So I assume the third module is going on this case. So advances in welding and joining technologies. In this particular subject, I have covered up the very basics of the welding processes. At the same time, the little bit advancement of the different applications area that is was also objective in this particular course, and I have covered all these aspects. But if you look into carefully, what are the course content in this particular course? First, the very basic understanding of the welding and joining processes, and of course, based on the scientific principle, what we can understand the processes that I've tried to explain. Then we focused on the laser and electron beam welding processes. So very specific because it is very important nowadays. You can find out that there's a huge application of the laser, and this in general called the high energy beam welding process. So that includes both laser and electron beam. Then we have tried to explain the solid state welding process, and solid state welding process is significant when there is a problem, difficulties associated with the fusion welding process. So that's why there is a development of the different perspective. The solid state welding process performs better than fusion welding processes. Then a little bit we cover up computational welding mechanics in this case. The how to do very simple calculation, heat transfer based on the heat transfer or other kind of efficiency, temperature distribution, that or stress maybe. So this kind of simple calculation we have tried to cover using in this particular module, the computational welding mechanics. Then we mainly focus on the micro joining and nano joining applications. So micro joining, we can find lots of application in medical devices or in that industry. So that's why I covered this micro joining process. It's a micro joining process is not very specific welding process. So it's maybe the scale down of the conventional welding processes, but application can be in the very small size components, mainly in the medical industry. So that I have tried to cover up in this particular module. And then we have discussed on the welding metallurgy. Metallurgy means the welded structure, the microstructure, how it forms, how microstructure depends on the this type of welding processes, and what is the role of the solidification behavior to form the different microstructure. This part is mainly discussed in this particular module. And then we spend one module specific to the non-metallic materials, because there is a plastic component or maybe plastic to metal components. So very other different kind of the non-metallic, for example, ceramic welding also. This type of welding process I have tried to cover in this particular module. And finally, nowadays, it's very important to develop the wire arc additive manufacturing processes. So what is the role of the welding processes, or how you can understand, how you can utilize your conventional welding processes or your knowledge of that to develop additive manufacturing or metal printing technology. So that part was we have discussed, but here most important part is the metal transfer mechanism. So that we first try to understand the metal transfer mechanism, because it is helpful to develop the additive manufacturing technology. So these are the overall content of this welding process, and we have decided the different kinds of the reference book also that cover up the different area of the welding process. It's not like that everything has been given in one book, not like that, but rather I can say that different topics are there in the different books. So for example, the reference one is more important if you understand the physics of the welding process. Same thing also, principle of the welding process, if you understand, then you could consult with the reference 2. But if you know more application on the micro joining and nano joining, in that case, reference 3 is the best book. Apart from this thing, you only focus on the laser materials processing, that means laser welding processes. There also the 4th book, reference book, is more important. Then this welding metallurgy, reference 5, it is most suitable if you understand these things, and if you do some calculation, analytical solution of the welding problem. In that case, the reference 6 is most suitable. And suppose you are interested in both in the friction state solid state welding process, maybe the friction state welding process. In that case, reference 7 is the useful book. Apart from this thing, what are the advances in the welding process? that can be better explained in the reference 8. Similarly, reference 9 also similar direction, computational welding mechanics. So that analytical solution of the different problem associated with the welding can be better explained in the reference 9. And finally, that additive manufacturing processes is that we can use the reference 10. So these are the, if you see the different reference books has been used to make this complete course structure, and all the different specific to the all the 10 different books having different specific area of working which is associated with the welding process. Now I have observed from the CR file that you have only introduced yourself, but I don't find any kind of the questions for these interactions so that I can answer all these questions. But I have prepared based on my previous experience, few questions I have prepared, and maybe we can discuss all these questions one by one. So this is a very common question that people ask, that what can be the pattern of the exam and what is will it be a multiple choice type questions based or pen paper exam. So it is very clear that first thing is that I think you are solving the assignment problem and you can see the particular problems in the assignment. So what is the structure of the assignments? We'll follow the similar kind of the structure in the final exam. Of course, it will be the multiple choice type questions and similar to assignment problems, and it will be online, not the pen paper based exam. It will be, everything will be online exam. Next part is that maybe some point of time that maybe raise these particular queries. If two materials with the different densities are welded, how will the weld heat formula gets changed? Definitely, if the two materials get different densities, or maybe the properties, other properties are also different of the two different types of the materials. In this case, usual procedure is that you can make the average values of these two materials, and then you use this average value to perform the to do the calculation and all this thing. But of course, it's a very simplified form. But if you, because when the two different materials are mixing and they are in liquid phase, mixing together, when they are solidification, then solidification behavior completely different on the different perspective. Therefore, it is when two liquid metals mixing, that it can form a some, I can say, some different material. So therefore, better the predict of these properties of this material, the averaging of the properties of the two materials. So this is the usual conventional approach to handle this kind of a situation. Then what will happen when we use the AC current for welding process? So that is also we'll discuss, but I think we have more on this PPT. So some topics we'll be discussing. Then what software is used for the simulation of the welding process? And I think in that case, industry also even asking this software can be used in the industry as well. I say yes, because we are using the finite element based software, and because finite element method we are using, and in that case, you can utilize the Abacus software, you can utilize the COMSOL software, this mail you can use, and even you can use the SysWeld that is specifically dedicated for the welding problem. But Abacus and COMSOL are more common problem. We can use it, but that are finite element based software. So you can use any one of the software to solve the welding problem or to perform any simulation, heat transfer simulation, stress analysis simulation that can be used. That can be done using this kind of the software. Okay, please explain polarity terms. Definitely try to explain the polarity term. Means of the more heat is generated in the electrode when in the workpiece. That we'll discuss. And then finally, can material of fixture will deflect. Basically, what I understand the final part is the basically relevant to the electron beam welding process. So when there is a dissimilar welding using electron beam welding process. So all this point I'll try to discuss here now. First, we look into the polarity. So we use the current, can be AC current, can be DC current also in a welding process. So for example, alternating current, every half cycle, the polarity changes. It becomes negative and positive, continuously changing over the cycle. So that means this type of welding process is used specifically the material, low melting point material, having very good affinity with formation of the oxides. For example, aluminium. Aluminium, very quickly they can form the oxides. So therefore, it is necessary when perform the welding process, remove the oxide layers. So that's why we can use the alternating current such that 50% heat will be generated on the workpiece and 50% heat will be generated to the electrode material. So that's why it is and that will help to both the cleaning action of the oxides layer and perform the welding process. So that's why AC current is most suitable for the aluminum or aluminum alloy. Now, if you look into the DC current, in this case, the simple way we can understand the DC current, and therefore DC current, you can use the direct current. Electrode can be positive terminal, electrode can be the negative terminal. So when electrode can be the negative terminal, the flow of the current, the flow of the current is basically, we can assume this is the flow of the electrode. So that electron will be attracted by the positive workpiece, because in this case, where if you look into the electrical circuit and electrode put in the negative and workpiece as a positive, then most electrons will be attracted to the positive workpiece. So when electrons will be moving towards the positive electrode, a positive workpiece, then kinetic energy will be released to the workpiece and more amount of the heat will be generated there. So roughly 70% heat will be generated on the workpiece and the remaining 30% heat will be generated to the electrode. It means that both are heat will be generated on the both sides. It is not possible to make one side 100% heat generation, on the other side there may not be any heat generation. It should not be like that. So therefore, in this case, when you use the electrode as a negative terminal and workpiece as a positive terminal, so maximum heat will be generated on the workpiece side. Other way, when you use an electrode as a positive terminal, workpiece as a negative terminal, in that case, of course, maximum heat will be generated towards the electrode side. Now, when you are using the consumable electrode, then definitely you will try to melt the electrode material. So in that case, you try to use the DC electrode positive. So that means direct current electrode positive. In that mode, we can use it. And in that case, workpiece will be the negative, because your objective is to melt the electrode material in case of the consumable electrode, for example, gas metal arc welding process. But if you use a non-consumable electrode, for example, gas tungsten arc welding process, your intention is not to melt the electrode material. In that case, you can use the electrode as a negative terminal and workpiece as a positive terminal. So therefore, so more heat will be generated towards the workpiece. So this is the basic philosophy of using to choose the polarity in any kind of the arc welding process. Then sometimes you ask the shielding and all these things, protective, what can be the role of the shielding gas? Why you can use the shielding gas during the arc welding process? So shielding gas we can use that, or I can say the shielding can be used just to avoid the contamination from the outside atmosphere during the performance of the welding process. So maybe when you put any steel or iron at room temperature, it may not readily react with the oxygen or nitrogen outside atmosphere. But when you melt the steel, it can easily react with the oxygen and make the oxides. So that reaction rate will be much more when it is heated or at very high temperature. So that's why when you try to do that, melt the material, at that time it is necessary to protect this molten pool from the outside atmosphere. So for that purpose, we can use the direct, either we can use the direct shielding gas or we can use the flux also. That flux can protect this molten material during the welding process. So both options are there. So we can use direct shielding gas, can be argon, helium, carbon dioxide and oxygen in this case. But you can ask why I should use the carbon dioxide and oxygen. They also make the oxides. But in this case, mostly we can use the choice of the inert type of gas. Argon and helium are the most preferred choice for the shielding gas. But sometimes we can use the carbon dioxide gas, because carbon dioxide gas maybe carbon dioxide is basically commercially we can use it because the matter of the cost, because in that type of gas the cost is much more as compared to the carbon dioxide. Because of that we can use this thing, but at the same time we can perform the welding process without much hassle or without much without forming of any kind of the contamination can be used. But oxygen can be used, because sometimes we can use oxygen, but the percentage of oxygen can be very, very low, and we can not possible to directly use the oxygen, 100% oxygen. Probably we can use the oxygen by mixing with the other inner type of gas, say argon and helium. and mixed with the oxygen, but oxygen percentage is very, very low. In that way, we can use the oxygen, but oxygen can, there might be different loads. So sometimes you can use the surface active elements, very small quantity of oxygen useful, and sometimes it helps to stability of the arc also. So for that purpose, we can use the inner type of gas mixing with the oxygen. So that options are also there. Now, sometimes we use the flux also. In that cases, flux can be used in this case, but flux that react with the molten material, and then it from the slag formation, and slag is lighter in weight, and it comes on the top of the oil pool. So that you can easily remove after solidification. You can remove the slag from the welded component. So that's why we can use the sealing gas, and that is the purpose of using the sealing gas. Now come to this point. Somebody asked about the metal transfer, which is important. The spray type transfer is basically. So we know the different mode of the metal transfer in gas metal arc welding process. So usually globular type of the metal transfer, short circuit metal transfer, and other is the spray type of the metal transfer. Now, in this case, spray type metal transfer, we use the welding current density is very higher than the globular type of the metal transfer. So very high current we can use. If you use the very high current in gas metal arc welding process, we can expect that it can create some kind of the spray metal transfer. Very small droplet can be used, droplet can be formed, and it will be projected on the workpiece surface. So in this case, this pinch force means because of the induced by the electromagnetic force. So that pinch force is more active to create the small droplets here and transport it from the electrode material to the workpiece. So in this case, for example, when you use the globular type of the metal transfer, in this case, the gravitational force is more important because droplet size is very bigger than the electrode diameter. So therefore, here, when this gravitational forces of the droplet is much more than the surface tension force, then the surface tension force can be considered as the drop holding force. Surface tension force will try to hold the drop. Now, when the gravitational force is more than the surface tension force, then in that case, the droplet transfer will occur. But in this case, the driving force is the gravitational force. But of course, you can ask that there might be some role of the electromagnetic force also, because in case of the globular transfer, electromagnetic force is there always. But in this case, may not play the role because electromagnetic force is basically try to detach the droplet from the electrode. So they are also having role, but I think more important force in case of the globular transfer is the gravitational force. Similarly, in spray type of the metal transfer, in this case, the electromagnetic force is more important because if the droplet size is very small, so therefore gravitational force is also less, and electromagnetic force will try to cross over the drop holding force, surface tension force, then only drop will detach. So therefore, in this case, the electromagnetic force or pinch force is more important in this particular case. But in the characteristics of the spray type of transfer is the droplet size is very small. And of course, it usually happens at the very high current density or by welding current. And every time we need to beat the surface tension force, then only droplet will detach from the electrode material. Now, sometimes we understand what is the heat content, enthalpy of melting, what is the, in case of the fusion welding process. So we can simply calculate this, what is the enthalpy of melting. It means that what is the heat required to melt a given volume of the weld. So here you can see the heat required when you try to melt, when you supply any arc to the substrate will try to create the molten zone. And assuming that this molten zone is basically the amount of the heat content of the molten zone will be like that. So heat required to melt the solid. That means initially it was solid phase, and when you are melting it, it goes to the from solid phase to room temperature to it should go to the melting point temperature of this particular metal. So that amount heat is required. Now once it reaches to the melting point temperature, then there is a phase change from solid phase to liquid phase. So in that case, we need the latent heat. So therefore, combination of the two heat content can be calculated as the total enthalpy of melting. So here we can see rho Cp and temperature difference. That means from initial temperature, room temperature to melting point temperature. That difference is there. specific heat and density of this material, plus latent heat to change the phase from liquid phase to solid phase to liquid phase. That amount heat also required. But here we are, one assumption is there sometimes in real welding process, the fusion zone temperature may not be exactly always the melting point temperature, though it can be more than that. So therefore, if we neglect the superheating temperature in this case, then this calculation is valid, or roughly you can estimate what is the amount of the heat required to melt the substrate materials. This will get some understanding idea that exactly what is the amount of the heat is required. So this simple calculation we can do. But one point, when you're looking into the latent heat of fusion, you have to look into the unit. Sometimes it may be necessary to multiply by the mass. It depends on the what unit is given for the latent heat of fusion in this case. Now, sometimes we discuss the advancement of the welding process just to understand the flow, fluid flow. So sometimes we neglect the understanding of the fluid flow in case of the fusion welding process, but some point of time it is important because it is having certain role in to decide the size, shape and size of the fusion zone. So in this case, what we understand when there is because in fusion welding process within the small weld pool, there must be the circulation of the liquid metal is there. In this case, the dominant driving force for the circulation of the flow of the material, liquid metal, that is because of the surface tension force. And surface tension, how can we measure it or how it is related to? Because surface tension gradient can change in presence of the surface active elements. So here the surface tension force can be changed in presence of the surface active elements. So that means the gradient can be positive to negative or other negative to positive. Some small quantity of the elements, surface active elements. For example, the sulfur or oxygen can add, but that is having some adequate quantity and it's very small. So any quantity of sulfur or oxygen may not act as a surface active element. They're very specific component or a very specific amount that actually acts as a surface, changing the surface tension force and act as a surface active elements in the weld. So therefore, when there is a change in the surface tension gradient, the change in the direction of the fluid flow in the weld pool, and when there is a change of the direction of the fluid flow within the weld pool or liquid metal flow, that actually affect the weld pool shape, and that will try to look into how it works. So here the right hand side you can figure in this case the surface tension force and temperature relation between the surface tension force and temperature, because surface tension force is a function of the temperature. We can see in presence of no surface active element, the gradient is basically the negative gradient. If you see the first figure, so when there is a negative gradient, then the liquid will try to flow. The surface tension force will be acting from center to towards the outer periphery. So when the clockwise circulation loop on the right hand side, we can find out, and that actually increases the weld width but decreases the weld depth. Now, if the surface tension force is by adding some surface active elements, then surface tension gradient may change negative to positive. And then when there is a change in the surface active gradient, in that case, if you see the fluid flow occurs from the anti-clockwise direction, if you look into the right hand side. So with respect to the center, the liquid will try to flow from periphery to outward periphery towards the center. When this kind of the pattern is there, then it will try to increase the weld depth but decrease the weld pool. So I mean to say that simply you can adding some kind of the surface active elements. It means that very small quantity of oxygen and sulfur, they can change the weld pool pattern. But how you can explain it? You can explain it just looking into the what is the how the surface tension gradient is actually changing, and based on that we can explain the effect of the surface active elements to change the shape of the weld pool. So, but this when you try to explain this phenomena, you need to consider the effect of the fluid flow. So there are different ways to add the surface active elements. For example, the chemical composition of the base metal. For example, the steel is already having some very small quantity of the sulfur. So that sulfur will act as a surface active element and change the pattern of the material flow pattern during the fusion welding process and modify the weld pool shape. Sometimes you can use the along with the fluxes, we can use this specific fluxes. We can use the oxides or halide fluxes on the substrate material that can act as a surface active elements here. Similarly, directly we can use along with the argon shielding gas, we can use the CO2 also. So here the oxygen can act as a surface active elements and change the pattern of the liquid metal flow within the small weld pool. So this is the different way the surface active elements can be introduced in the fusion welding process. And based on this concept, the industrially activated T-welding process has been developed. Now, activated T-welding is a variant of the T-welding process, definitely. And here we can use the very thin coating of the activated flux, 10 to 15 micrometer, just simply painting over the surface on the joint area before the welding process. Then we can perform the welding process, single pass welding process, and that will try to increase the penetration because of the effect of this active coating, surface activated flux over the surface. So this actually helps to perform the very high thickness welding of the very high thickness material using simple GTAW process and using single pass, not the multiple pass. Therefore, it may be reduce the consumption of the filler wire because we can achieve very high thickness using this process. So therefore, we can reduce the use of the filler material. At the same time, residual stress can also be reduced significantly in this particular process. And based on that, we can say that significant cost reduction in the cost of the fabrication is possible using the activated T-welding process. Now coming to this point, that electron beam welding of the dissimilar material. If you observe that electron beam welding is usually used very high thickness material, the thickness is very high. In that case, you can use the electron beam welding process. Now, assuming that material A and B, these are the two different materials, their magnetic permeability are completely different. Now, when you perform the electron beam welding process, you focus on the electron beam on the top exactly at the interface. Then what will happen up to certain distance, at a certain depth, the beam gets deflected towards any one of the materials. Either it will be deflected towards the B material or it can deflect towards the A material. But there must be some deflection because in this case, deflection will happen because of the Cback effect. So that means it happens in practical when two materials are dissimilar materials and their properties are different. But of course, the combination of the materials, what will be the angle of the amount of the deflection, it depends on what are the difference their properties between these two materials. Mainly the magnetic permeability of these two materials. There is a huge differences, then deflection might be more. The less differences, then deflection might be less also. So, but what is the principle? What is the physics behind this thing? Because this is the effect of the Cback effect. How you can understand the Cback effect? Cback effect in this case, we can see that when two different materials, they maintain the different temperature at a junction. So basically properties are different. So definitely the two material, even if you're heating material, they can achieve the two different temperature at the junction. So when there is a two different temperature, they will induce some kind of the electromotive force. EMF will be generated, and that EMF will be generated that can be calculated equal to Seebeck coefficient S into delta T. Delta T is the temperature gradient. So that will help you to calculate what can be the amount of the electromotive force will be there. So definitely when the electron beam is the flow of the electron and it will be affected by the electromotive force. So when the electromotive force will try to deflect the beam one particular direction, but it entirely depends on the property differences between the combination of the materials, and it is very applicable in case of the dissimilar material of electron beam welding process. Actually, it is a problem associated with the dissimilar welding of the electron beam welding process, and this problem is more severe when thickness is very high thickness you try to join using the electron beam welding process. Now we try to look into three different combination of the materials. Say for example, iron and copper, stainless steel and the low carbon steel, and low carbon steel and the nickel alloy steel. This combination of the material you are trying to join using the electron beam welding process. So in that case, okay. So in that case, depending upon the magnetic permeability, the shift can be, but the degree of deflection depends on the combination of the material. I mean to say that it's not necessary that all three combinations of the material will be deflected the same angle. All three cases, the deflection angle will be completely different. Now, this is very important. So just an overview of the comparison between the laser and electron beam welding process. So this case, different perspective if we consider, then there is a difference. For example, if we consider the weld zone and heat affected zone size, shape, both the cases they can follow that narrower welding or the very smaller weld zone or heat affected zone, and even laser also. But it at the same time it depends on the this what type of the laser we are using in this case. But as compared to the arc welding process, this weld zone and heat affected zone is very narrower or very smaller. So this is the first comparison. Then depth of penetration. Basically, electron beam produces a very deep penetration. The penetration is very, very high. It means say that very high thickness material can be welded using the electron beam welding process. But on the other side, laser also lack of penetration is means here with respect to arc welding process. With respect to electron beam welding process. But of course, laser also depth of penetration is very high. So you see when you are following the keyhole mode. But as compared to the electron beam, it will be less. Welding speed. Because electron beam welding process, we can use the very high speed. We can move the torch at very high speed to perform the welding process. But in case of the laser welding, relatively less as compared to the electron beam welding process. Because if you see it actually depends on the what is the amount of the heat transfer to the workpiece, and that is related to the what is the power, electron beam power or laser power divided by the velocity. So, and because input electron beam power can be much more, because efficiency for the electron beam is very, very high as compared to the laser, because laser efficiency is very low. It can be 10 to 20%, and electron beam can be 80 to 90%, can go like that. So that's why electron beam, that means heat input can be much more for the same power of the laser and electron beam. So that means electron beam can be used at very high speed to perform the welding process. Shielding gas, electron beam welding, it is not required because it performs under the vacuum, but laser welding will use the nitrogen or argon shielding gas. Can be used. Vacuum chamber, in case of the electron beam, it is mandatory, it is required, but that is not required in case of the laser welding system. Cost, definitely cost is electron beam welding system cost is very, very high as compared to the laser welding system. Generation of the X-ray, because in case of the electron, because of the secondary scattering of the electron, it can produce the X-ray. So that is one of the problem, or maybe not problem, the disadvantage of this thing. There might be possibility of the formation of the X-ray generation in the electron beam welding process, but that kind of the things are not possible in case of the laser system. Power efficiency is more 80 to 90% for laser electron beam, but laser welding efficiency can be 10 to 20%. Size of the workpiece. So because electron beam perform under the vacuum, the size of the workpiece is limited by the size of the vacuum chamber. So that will decide what kind of size of the components can be handled using the electron beam welding system. But that kind of the limitation is not there in case of the laser welding system. So this is the very basic parameters. What are the difference between the electron beam and laser beam welding process? So that's all. Thank you very much for your kind attention. Now we'll discuss about the any like questions. If you want to discuss, we can discuss it. Okay, so I think live interaction there. Anand Power. Okay. What is difference in the current and the spray type droplet material transfer? Okay. So what I understand this thing, in case of spray type, current for spray type and droplet material transfer. Okay. So spray type and droplet means basically what you understand that it's a globular type of the metal transfer. And the spray type, globular type of metal transfer, the current requirement or current density is low, but spray type transfer, the current density is much more. We use the more current. So if you use the more current in GMAW process, then in that cases, it will try to produce the spray type of the metal transfer. Or if you use the less current, then it will try to produce the globular type of the or droplet type of the metal transfer. Now, this metal transfer, but rate of the metal transfer is basically controlled by the feed rate of the electrode material. So feed rate of the electrode material decides what can be the rate of the metal transfer. Okay, and that not depends on the mode of the metal transfer, but feed rate decide the rate of the metal transfer. Now, it actually affects the heat affected zone because spray type the transfer, the heat affected zone must be much more because it's spread over a bigger area or bigger domain as compared to the droplet, because droplet will transfer, because of the droplet transfer is a relatively slow process. So therefore, it will exactly one particular position, maybe because of the weight means basically gravitational force, it will drop one particular position. Surrounding, it says spread is kind of the projected transfer, so it can go bigger area, it can spread over bigger area because current density is very high. So in that case, the heat affected zone might be different in these two cases, but it can be exactly this theoretically I can say like that, but if you want to see how differences, definitely, but difference must be there. But what extent the difference might happen, that can be say only after doing some kind of experiments on that. So any other questions? If there is no questions, then I can stop here. I don't find any other question, then I stop here. Okay, so I stop here. I'm just leaving this platform. Thank you. Thank you very much for attending this.